Like, am I unmuted? Um, Thanks a lot. Okay, well, let me make sure I can screen share before I get like too far ahead of myself. Um, Boom. Do you see just the slide? Okay, let me just get all my stuff set up.
Recording in progress.
Okay. Um, Excellent. Well, I'm very, very excited for this. My name's Charlie. I'm here to talk about Ruff. Um, I I don't really give a lot of talks, and I definitely don't give a lot of talks to Rust oriented or Rust specific audiences. So this will be entirely new material, which is good and bad probably. It's good in that it'll be totally original, and you're all the first people to see all of this content. It's bad in that I'm sure it will feel a little bit unrefined, and I already know that I'm trying to cover too many disparate topics, but hopefully everyone will find something interesting. The way that I've structured this talk is, I think sort of like what Ruff is probably the least interesting thing to people here. They're probably more interested in how it works and how it was built. But I am going to start by talking a little bit about what Ruff is and how it created. Then I'm going to talk about how Ruff works. And then at the end, I want to go deep on performance and some of the specific things that we've done in Ruff to improve performance. Because I was looking back at my old code, and this is where I found all the really interesting things that I've learned over the past year or so working on Ruff. So the talk will get increasingly specific as we go on, and at the end, we're going to look at some actual code and talk about very specific changes that we made in Ruff, the impact that they had, and why. Okay, so let's start by talking just briefly about what Ruff is. So I have this line in the front, an extremely fast Python linter written in Rust. So Ruff is a linter. It lints Python code. So it looks for problems like unused imports, unused variables, but it can also do things that are a little bit more, I guess, advanced than that. So it can do that kind of semantic analysis, but it can also make suggestions like, oh, you're using an old syntax to express this idea. You can use this newer syntax. And it will also automatically rewrite your code. So if you've written Rust before, Clippy has a pretty powerful like auto fixing and code rewriting system. Ruff does a lot of that too. So it's really seen as a linter and a code transformation tool. Importantly, Ruff is like entirely written in Rust, but it's installable through pip. So you don't need to have Rust installed to use it. It distributes like any other Python package. I'll talk about that a little bit more as we go on. Ruff is, in a very short time, has grown to be used by a very large number of projects. So the first commit to Ruff was, I think, in August of 2022. So it's been a little under a year. And it's now in use by a bunch of big companies. I would say like most of the sort of bigger Python projects that you might have heard about or seen on GitHub. So in a very short period of time, we shipped this weird Rust-based like Python linter tool, and people really gravitated towards it. This chart's actually really dated. This is from when I did our company announcement post, but we're now, I mean, this is just GitHub stars, but we're now above the top of the y-axis on this graph. I guess the other important thing that Ruff is to me, Ruff is the first tool in a tool chain. So Ruff is a linter, but it's also kind of an embodiment of this idea that we could make very different Python tooling. And in this case, very different meant a few different things that I'll talk about, but one obvious one is performance. So to me, rewriting this linter stack in Rust created this tool that really resonated with people, and clearly a lot of people found it useful and valuable. I started a company, Astral, based on that idea. Our goal is to build more Ruff-like things. So we're trying to build more Rust-based Python tooling. So where did Ruff come from? Why did I build this thing? I think I'll answer this by answering a slightly different question, which is where I came from, like what's my background? So I started my career at a company called Khan Academy, which is an education technology company. And there I worked on a lot of things that were not Rust. So I did a bunch of web front end, like a lot of JavaScript. I did some web backend in Python. I did like a year-ish of Android when we started building, or Java, when we started building our first Android applications. I did a little bit of iOS. So I worked across a bunch of different programming ecosystems on like a bunch of totally different things, just kind of, I think, hopefully learning to be like a somewhat competent generalist software engineer. After that, I joined a company called Spring Discovery, which is a computational biology company. And this was like totally different work. I was building a lot of machine learning infrastructure. So that was all Python. A lot of data infrastructure. That was primarily Python. And then at the end, started to be this sort of hybrid Rust and Python code base. And again, I was doing a lot of front end, this time in TypeScript. And there were a couple things that led to me starting to work on Ruff, as I said, in August 2022. So, I guess the first is like, I wouldn't say I've had like a super long career or anything, but I have worked on in a bunch of different programming ecosystems. And I think that influences how I think about tooling. I look at things that certain ecosystems do really well. And then when I move between stacks, I find that I'm missing things. And in this case, even I felt like web tooling or Rust tooling, when I was coming back to Python, I was feeling frustrated with some of the edges that I was running into and the inability of the tooling to scale to our project, which wasn't enormous, but was big enough that things like our linter, our type checker, we were having to really become experts in how to do package management in Python, and all those things to me felt a little bit off. I think the other things that contributed to me sort of thinking about building Ruff was that we started to use Rust at Spring, as I mentioned. And that was a totally new thing for me. I think this sort of resume shows like I do not have like a systems programming background by any means. I wrote some C in college, but I've never written any C++. I've never written any like professional grade C. And so Rust was a really new thing to me. It was my first brush with, I guess what people would call like a systems programming language. And so getting exposed to that at work, to me, it was just interesting that it felt accessible, even if I didn't really understand the language, that I could kind of build stuff in this new language and I could build programs with like really, really different characteristics from the things I was used to building. And then I guess the other thing I started to see was that more and more tooling, especially in the web, was being written in not JavaScript. So like more and more JavaScript and web tooling was being written in Go or Rust or Zig. And I started thinking about whether we could apply those same ideas to Python tooling. So could we build Python tooling in not Python, I guess is the way to put it. And what would that look like? How different would it be? And Ruff was my attempt to answer some of those questions and honestly to learn Rust. Like I didn't start Ruff with the intention of turning it into the project that it's become, and certainly not turning it into a company. I really started Ruff with the goal of trying to learn Rust and get better at Rust, and also see if I could prove out some of these ideas around building really different Python tooling. In March, ish, I guess I think we publicly announced the company in April. But I started a company, Astral, which is really based around the ideas of Ruff. So we're now a team of, we're a team of 5, and we're working to continue building, hopefully, really great Python tooling. So building more Ruff and building more Ruff-like things. I guess the other thing that I want to point out just by talking through this history is I've only been writing Rust for like about a year. So I suspect there are people in this audience who are like a lot more knowledgeable than me on Rust and on like specific topics on which I'm going to opine. But I still see myself very much as like on my own Rust learning journey. I'll talk about this in more detail, but Rust to me is really an amazing language, but I think it's also a language you can like learn many times over. The Rust I write now is like completely different from the Rust I wrote a year ago, and hopefully the Rust I write in a year will be completely different from the Rust I learn now. So my first slide was talking about what is Ruff. To me, that's also not really like a super interesting question. I think the more interesting question is like, what makes Ruff good? I talked about how like a lot of people are using Ruff. What's interesting about it? So the kind of headline feature is that Ruff is just really fast compared to a lot of the other existing tools. So we have this benchmark in our README. I think this is dated because I think we're actually faster than this, but this is the thing that I have nice and pretty and laid out and measured. So this is Ruff running as compared to a bunch of other tools, just with its default configuration, no caching, nothing like that. So Ruff is really comparatively very fast. I have this nice, I don't know if we're calling this a tweet still or not, but I have this nice note from Nick Schrock, who's the co-creator of GraphQL. He runs a company called Elemental. And he talks about how Ruff it for them was 1,000 times faster. So on their code base, it used to take 2.5 minutes on his local machine to run Pylint, and now Ruff runs in, I guess, 400 milliseconds. And he had there's another tweet in this thread where he talks about how on CI they would like parallelize across all 70 Python packages that they publish. They would run like a separate CI job, and now the whole thing runs as a pre-commit hook. So Ruff is like fast enough that the ergonomics of using it are very, very different from other tools that you might switch from. And we're going to talk a lot about what makes Ruff fast, because I think that's a very interesting question. Second thing that I think makes Ruff good and interesting is that I use this word like unified. So the thing that we tend to see is that people come in with requirements.txt, basically dependency lists that look something like this. They have like a ton of different dependencies this is all static analysis code quality tooling that's either like linting or import sorting or doing something, or formatting or doing something else. And then they come out with something like this. This is like a real thing from the Discord. So they went from like, I don't know, like 30 dependencies to like just using Ruff and their auto formatter. And we're actually working on a Ruff auto formatter, so maybe this will become just Ruff soon. But the point is, Ruff, it sort of bundles a lot of the things that you might want in your linter that would traditionally all be done by separate tools in Python. So like import sorting, for example, Python typically uses a separate tool for that called isort, but Ruff just treats import sorting as a lint rule. And so Ruff can replace your import sorter. And that same logic applies to just a bunch of other tools. So one nice thing that people see is it like really, really simplifies their not just their dependency list, but they only have to learn like this one tool, and it has all this different functionality bundled into it, which is something that people seem to appreciate a lot. I mentioned this earlier, Ruff does a lot of code transformation. So it's not just flagging errors, it can also automatically fix them for you. So this is just an example from something I was doing like over the weekend. In Python, if a variable or an import is only used as a type annotation, there are actually ways to avoid having to import it, which can make your code faster at runtime and reduce dependencies. Because here, for example, you actually don't need to import pandas to run this file. You just need pandas because you need to use the type annotation. And so Ruff can actually like identify imports and variables that are only used in typing contexts, and it can move them into these typing only blocks, and it can quote the annotations and do all this transformation for you automatically. So we're trying to get like more and more advanced over time with the kinds of, this is in addition to things like removing unused imports, which are comparatively much simpler. But over time, Ruff is trending towards being a more and more powerful code transformation tool. So you kind of plug it into your stack, and not only does it identify a bunch of problems, but it can hopefully fix most of them too. And then lastly, I mean, all the other Python linters, like thankfully, have this property too, but I guess it's worth mentioning because Ruff is written in Rust. So Ruff doesn't have any dependencies, like it doesn't depend on Rust to use it. You just install it with pip. We ship basically a single executable binary, and that gets packaged as a Python package using a tool called Matrin. This is actually, to me, a very cool property. You actually don't even have to install Python to use Ruff. So you can just drop in like a Ruff executable anywhere and run it anywhere. And it's just a standalone piece of software that you can install and use, just like if it was written. Well, if you're used to Python, then it just feels like you're using something else from the Python stack as opposed to being written in Rust. So let's talk a little bit about how Ruff works. And I feel like I'm going to do a really bad job with this section because I'm going to try and cover what I think are a lot of interesting ideas. But you can give me feedback afterwards about whether or not any of this makes sense. So Ruff is about 150,000 lines of Rust, split across 20 crates. And it's really structured as, the language here is very intentional. It's structured as sort of a traditional batch compiler. So you can view it as a compiler that like takes in Python source code and outputs diagnostics. I guess it also transforms Python source code, but let's just run with that sort of simple framing. So if you think about Ruff as a compiler, like the Ruff sort of compilation pipeline looks like this. We first discover all the Python projects in, all the Python files in your project. Sounds very simple, actually kind of complicated because we support this sort of, any file could have a different configuration. We support like hierarchical configuration. So you could lint a monorepo, lint a bunch of different packages. They could all have different configurations. So as we traverse over your project, we have to sort of map the configuration. And then we have a very, very simple model, which is that for every single file in parallel, we lint it. And that means read the file from disk, tokenize it and parse it. So break it down into tokens like keywords and variable names, parse it so we can identify, this creates the abstract syntax tree if you're familiar with that. So we get a representation of like, what are the function definitions? What are the imports? What are the function calls? And then we analyze that that tokenized and parsed representation. So we have we support lots of different kinds of lint rules, and like the inputs that they take can be different. So for example, we have some lint rules that only need to look at comments. Like if you want to make sure that a Python script has a shebang, you only have to look at comments. So you don't actually need the abstract syntax tree for that. You just want to look at all the comments in the program. So we have some rules that are just based on the token stream, which is like things like comments or like individual pieces of syntax in the program. And then we have a bunch of rules that are based on traversing and understanding the syntax tree and doing semantic analysis at the same time. So semantic analysis would be for things like unused imports. So to understand whether an import is unused, you need to be able to do a couple things. You have to be able to traverse the AST, identify the imports, and then keep track of them as you traverse over the rest of the AST. So you're trying to see, was this import referenced here? Was it referenced here? Was it referenced anywhere? So we traverse over the AST. We kind of build up this model of what are all the symbols? What are the function definitions? What are the variables? Where are they defined? What are the imports? And then what's used where? So you could think about this in the context of the example I showed before of like moving and quoting that pandas data frame type annotation. We need to do like a lot of semantic analysis to support that, because we need to know what are all the symbols that were imported, where were they used, were all the places that it was used, were those only type annotations? And then when we want to fix it, we need to know what are all the locations in the code where it was referenced, which of those need to be quoted. We had to import something, the from typing import type checking thing to move the import. So the point is, there's a lot of analysis that has to happen in order to support those kinds of rules, and that's where the bulk of the complexity and the sort of quote unquote linter lives, is in traversing that AST, building up a model of what's happening in the code, and then enforcing rules on it. After we like generate all the rules, we apply any of those automatic fixes, and we have a really, really simplistic model, which is that if we apply a fix, we just relint the file. Because you can imagine that like if you have an import that's used in one place, and then for whatever reason we've removed that usage, like, oh, that's not an expression that's that's not a function that's ever going to be called, and we remove it, suddenly you're left with an unused import. And so the way that we saw basically fixing one lint rule can lead to other lint rules being surfaced. And because we have this implementation where every rule operates independently, Ruff just has a super simple model of if we apply a fix, we just like rerun Ruff entirely over that file until it converges. And obviously that could, if you have a bad rule, you could end up running Ruff infinitely. We have a sort of cap of how many times you run it, and then we spit out a nice link to our issue tracker asking you to file a bug if you have some sort of infinite loop in your fixer. But this is a really, really simple model. We lint every single file independently, and we just lint and fix files until convergence. And then at the end, we print out all the remaining diagnostics. So we might, and that'll include code frames. So we'll say like this import was unused. Here's what it looks like in the code, all that kind of stuff. So this is like really, really simple, or not simple, but it's certainly not simple, but it's high level description of how Ruff works today. I think one interesting thing that I've been thinking a lot about lately, and this is weird because I'm like, I don't know that I'm trashing my own tool, but I think a lot about like how Ruff could work. And it's funny for me because I started working on Ruff. I didn't really know anything about building tooling like this, and so I just set off to like build a linter. And since then, I've learned a lot more about building tooling like this, and I've looked at a lot of other projects. I think the two that I tend to draw, I guess the most inspiration or sort of learning from with regards to like the high level design are Rust Analyzer. If anyone has used that, it's like the VS Code, typically used in VS Code. It's a Rust language server, so it sits in your editor and it handles like auto completion and a ton of other stuff. Super impressive piece of software. So I think about Rust Analyzer, and then I think about a project called Rome, which is a unified tool chain for the web. So it's like JavaScript, TypeScript, et cetera, also written in Rust. And they have that I think is an extremely well-designed piece of software and has a lot of similarities to Rust Analyzer. But I want to talk for a second about things that Ruff doesn't do that like those pieces of software do that are kind of interesting to me and may hint towards like what we want Ruff to be in the future. So the first is that I talked about how Ruff is a batch compiler. This is as opposed to what I've seen called like a query-based compiler. And this is the kind of thing that you would want for a language server. So imagine that you're a Rust analyzer and you're sitting in the IDE. So someone like opens up a Rust file, and there's a couple things that you like don't want to happen. So one is that you don't want to have to analyze like their entire project and code base in order to provide like any information. The other is that when they start editing the file, you don't want to have to rerun all of your analysis in totality just to provide updated information and inference. Like when someone opens a file in Rust Analyzer, you want it to be highly incremental. So you want to say like, what's like the minimum information I need to provide context on like what's happening in this file. And similarly, when someone edits a file, you want to do like the minimum amount of work required to get to new insights. That's like a really, really different model from how Ruff works. Ruff has none of that incrementality built into it today. It is every time that you run Ruff, we basically analyze your project from scratch. That's like a really different model from something like a language server. And Alex Kladov, or Matt Clad, who wrote Rust Analyzer, he has like the greatest blog of all time. If you're interested in learning Rust, like every single post on that blog is worth reading. But he's also done this whole video series about how Rust Analyzer works. And the biggest takeaway for me is that like building something like a language server is really different from a traditional compiler because of these ergonomics. It's a long-lived piece of software that's like sitting in the editor, and you're always trying to do this incremental work. Ruff does not work like that today, and maybe it will someday. But to me, that's like a really interesting design problem and constraint for software. Like building a language server versus a traditional compiler, very, very different. I guess the other thing that is worth mentioning there that I'm realizing I don't think is on the slide anywhere is that like Rust Analyzer, for example, can parse invalid programs. So think about when you're like typing in your editor, like you're introducing a lot of invalid states, like as you're in between syntaxes, like you're starting a function call, you hit the open parenthesis, you hit save. Like Rust Analyzer does a good job of trying to parse the program, even if it's not syntactically valid. Like it basically makes its best effort at understanding what the syntax is trying to be. And then it provides diagnostics based on that. Ruff does not do that. Ruff can only parse valid programs. So again, I'm kind of talking down my own work, but there's a lot of interesting stuff that you can see in these other pieces of software that I think Ruff could become. We only work on Python files. We also support like Jupyter notebooks, which are a little bit different, but it's still ultimately parsing Python source code. That's as opposed to something that would be language agnostic. Ruff only operates on the AST and the token stream. We don't use what's commonly called a CST, which would be like a concrete syntax tree. This is kind of a small thing, but Rust Analyzer, for example, uses a CST, which means that like everything in the code is captured in the AST, like comments and white space. Our representation, our AST doesn't capture those. This mostly impacts Ruff internals and not externals, but it's again just one difference between where I think Ruff could become or how like Rome and Rust Analyzer works. We also do this like rerun until convergence thing, which means that every time we edit your file with an autofix, we then reparse the file. So like we removed an import and now we have to reparse the whole thing. That's like super inefficient because you can imagine a fixed model where you're actually changing the syntax tree. Like imagine that instead of removing the import and then reparsing a file, you just remove the import from that abstract syntax tree or that concrete syntax tree. Then you don't need to reparse, you just reanalyze and reanalyze. So these are kind of like idealistic things that I think about sometimes with when I think about how Ruff could be designed differently, which is a weird thing to include in the talk, but I think helps point out some of the things that makes this kind of working on these kinds of problems quite interesting. All right, so rest of the talk, I want to focus on like what makes Ruff fast, and I'll talk a little bit about some of the sort of high level, some of the high level properties of Ruff, and then I've queued up a bunch of specific PRs that we made that made Ruff faster, and I kind of want to talk through what those are and like why they made Ruff faster and what the lessons were. I don't know how many we'll get through. We'll kind of see when it starts to feel like really boring because I think I probably queued up too many. But we'll just see how long it remains interesting. And I guess I'll be the judge of that. So the first thing that makes Ruff fast as compared to a lot of other tools is we parse once. So we have unified tooling, which means that we only need to like parse well, ignore the fact that we might reparse it after we fix it. In general, we parse once. So Ruff does a lot of different stuff. If you look at that first screenshot of like, oh, I'm using 20 or 30 different Python static analysis tools, many of those have to parse the code themselves or come up with their own intermediate representations of the code. So for example, if you're using like flake8 as your linter and isort as your import sorter, and then pydocstyle as your docstring linter, each of those are going to end up parsing your Python source code. Even though they could benefit from the same intermediate representations of it, like that abstract syntax tree. So it's not just that Ruff is like faster than any one tool, it also scales very well as we add more functionality to it as compared to adding more tools. Like it's very hard, like if you just look at like a standard Python static analysis tool chain and look at all the different tools and count up how many times it's going to like lex, parse, read the source code from disk, it's a lot. And Ruff does that one time and then gets to benefit from that shared representation. So similarly, we're working on an auto formatter now. We'll still parse your source code once. We'll parse your source code once, and then we will like lint it, traverse it, format it without having to keep doing the expensive steps of reading from disk, parsing, lexing. So this is like inherent to the design that you get good economies of scale from bundling tools together, is how I would describe that. The other is that Ruff, I use this word around Rust before, this like fearless concurrency. Like we just have like a really, really parallel model. And that comes with limitations. By parallel, I mean that every file, we don't lint every file at once in parallel, but we can just completely parallelize the step of linting because every file is analyzed independently. That introduces a bunch of constraints, but my point is we can use a lot of parallelism, and Rust's parallelism, in my experience, is like way more efficient than, for example, Python's multiprocessing. The other thing that makes Ruff fast is just Rust. And this is a little bit nuanced. Like Rust is very fast, but like writing your program in Rust doesn't guarantee that it will be fast. It is definitely possible to write very slow Rust programs. But Rust gives you an extremely high ceiling for performance. Like you can write extremely performant software. And if you're doing, the exact same operations in like Python versus Rust, you should definitely expect the Rust version to be faster. And then Rust also just creates a totally different ceiling for how fast your program can be. And we'll talk about that in more detail. The other thing I've been thinking about a lot is like this idea of writing like performant Rust, I think is its own like area of expertise. And I'll demonstrate this in a second with some examples, but you can look at the same code like a year on, 2 years on, and you'll just look at the performance characteristics of it in a totally different way. There's just a lot to learn about like writing performant Rust. And not all of that is like specific to Rust. It's more specific to like data-oriented programming or whatever you want to call it. It's like, how do you think about the stack versus the heap? How do you think about caches? How do you think about when it makes sense to like do repeated work versus using more memory? Like these are general principles, but Rust just gives you basically complete control over them. And that's extremely powerful. I wouldn't say that I'm like the world expert in writing performant Rust, but like I do think Ruff has gotten a lot more performant over the past year, and I think my expectation is that it will continue to get much faster because of this. There's just such a high ceiling for how you can make your programs faster. And then the last thing is really, it's kind of cultural. It's like we just have a constant focus on performance. So we constantly benchmark, and that both means that we're like benchmarking on CI, and whenever we think about a change that we think will improve performance, we will never make that change without data. So we're always looking at micro benchmarks. So let's just analyze this one file a zillion times and see what the percentage changes are, and then we'll look at macro benchmarks. So if let's run Ruff over a large code base like Apache Airflow and see how much change there is. We have a very data-oriented approach to how we choose what to change, and a very performance-oriented culture in code review. So even small things that almost certainly don't matter, we will think about them at the level of what's a fast way to do this? Where are we doing unnecessary work? I guess one sort of aside, if you look at how Ruff works today, it's like impossible to put numbers on these because it completely depends on the project, the size of the project, the settings. Like Ruff supports like 600 rules, and most people do not enable them all. But if you enable them all, the numbers here change really dramatically. But I think this was with like the default configuration, which is a pretty limited number of rules. And I think I ran this over Apache Airflow. But if you look at like, and these numbers don't add up to 100, by the way, I know that. But if you look at this, like some time is spent like basically doing a bunch of IO to find and read all the Python files. A lot of time is spent on tokenizing and parsing. And then a bunch of time is spent on actual analysis. The rest of the time is like lost in various small places. It's like allocating and dropping memory, all that kind of stuff. And the funny thing about this for me is that like this to me actually says that like Ruff could be like way faster, because we have spent by far the least time on the parser, the lexer and the parser, where we're spending a lot of time. That is the place we've optimized the least. So it's just kind of a funny observation that Ruff is very fast, but I actually think that Ruff can be much faster than it is today. And I actually expect Ruff to get faster and not slower as we add more behavior to it. Okay, so I guess everything now has been like a little bit high level, but I want to talk about some things that make Ruff fast in practice. And these will not be large architectural things, but these are small changes that we've made over time to make Ruff faster. And the motivation for this actually came from looking at this really old pull request. So this is from, I said I started Ruff in August of 2022. This is from August 31st, 2022. It's PR issue, I guess PR number 53, and we're now on like 6,000. So this is like a really old change. And it's not my pull request. This is a contributor contributing this change on top of code that I wrote. And what this code is doing is it's trying to identify duplicate variables in function definitions. So if you had like def foo a, like you use the variable name a twice in your function definition, this rule would catch that. Actually a strange rule because that is a parser error in Python. So I don't know why we had this rule or why maybe we still have this rule, because I don't think that you can actually parse a Python program that will produce duplicate argument names, but we're not focused on that. That's not important. We're focused on what this is doing and how it's written. So the way this code is structured is we're going to iterate over all of the function arguments, and we're just going to put them in a hash set. And then if we see that we found, we've already seen an argument before, we're going to add a diagnostic that says we found a duplicate argument. Here it is. Here's what the duplicate argument is. This person came in and submitted a pull request that improved the performance of this check quite significantly. And the way that they're doing it is that they're avoiding these extra allocations by going from an own string to a string slice reference. And this change, I'm going to talk about that specific change that they made here in more detail, but this to me was really interesting because I looked at this and I knew that at the time when I wrote the code, like this to me is a really, really obvious thing to do now. But at the time, I had no idea that like this would be better performance. Like, that this would improve performance, or that this was even like the same or allowed. Like I didn't know any of those things. Like I had no idea what I was doing. And someone came and put together this PR, and I was like, oh, okay, this makes a lot of sense. And I kind of learned this thing. We committed the change. But looking at this now, not only is like the first version that I wrote in red, like to me, very inferior, but I can see like a bunch of things you can do to improve performance of this even further that were not obvious to me at the time, clearly, because I didn't do them. So I want to go through like 7 different versions of this exact same function. And each one, we're just going to talk about what's changed, and then I'm going to benchmark them all at the end. This is the first version of that function. It's basically what was in red on the slide before. So we're looking for duplicates. We're taking in, ignore, if you're a Rust expert and you have problems with specifics of this function signature, don't worry about it. It's not important for this. But basically, we're iterating over a slice of owned strings. And we're just going through each one and we're saying, is this in the set already? If so, we found a duplicate. Otherwise, put it in the set. So the first change, which was what we saw in that pull request, was that we switched, and I'm just going back and forth here a couple times. So this was the previous version, this is the new version. So the main thing is we switched from using an own string, that capital string, to a reference, the and str. And that means we don't have to clone the string down where we have scene.insert. So we went from having to clone, which means that we're performing an allocation, to just storing a reference to it. Allocating memory, pretty expensive. And this is one of the things we avoid as much as possible in Ruff. We make very, very few allocations. But in general, like if you can avoid allocations, you will tend to improve performance quite a bit because allocating memory, again, is expensive compared to not allocating memory. And so if you can do things that you can do on references, although it tends to make the code more complex, you have to really like think in Rust because you're now thinking about references and ownership. And like, I mean, you had to think about ownership before, but avoiding allocations, this was like the first thing that you can do to make this thing faster. The second thing, I want to make sure I get the order right. Okay. The second thing you can do is if you understand the Rust's set and map APIs, I don't know what this is called, maybe like the entry API, you can actually do one fewer operation here. So here we're checking if the argument is in the set, and then we're inserting it. But Rust API actually tells you whether an entry already existed in the set when you insert it. So rather than doing this contains and then insert, we can actually just do the insert. And if the thing was already in the set, Rust returns false. I'm pretty sure. It's not true. I'm pretty sure it returns false. Anyway, the point is we're doing a bunch of needless work, because to do this versus this, we have to hash the string twice. We have to do 2 lookups or insertions, whatever else. It's way faster to just do it in a single operation. Again, this is the kind of thing that I would now look at and say, this is super obvious, but I had no idea that the API worked this way when I first wrote this function. Another thing we can do, which is, this one's like, I don't want to call it free, but like, you can use faster hash functions. So this is a little strange because I was using btree set, which I don't really want to go into the details, but that's part of the standard library. But Rust also has a hash set, and they're subtly different. But there are Rust's default hash set uses a hash function that is not optimized for performance per se, and the reason for that is that it is more resistant to collisions and other kinds of problems that might be associated with hashing. And there are other hash functions that you can use that are much faster, especially when you're dealing with small keys. So if you're dealing with like integer keys and things like that, fx hash set and fx hash map are what we use pretty much everywhere in Ruff. And I believe Rust C, the Rust compiler itself, uses fx hash set, because in the context of a compiler, the things that you care about with the hash function just tend to be very different from what the Rust standard library optimizes for. So using a faster hash function can actually provide like very noticeable speedups depending on your data. The other thing we can do is if we, again, I talked about how, well, when you insert stuff into a hash map or a hash set, it will periodically has to grow, because it starts at a certain size, and then as you insert things, it tends to effectively like double whenever you hit the limit. So maybe it starts by having a capacity of 1, it allocates for like 1 spot, and then when you insert something, it doubles to 2, and then to 4, and then to 8. That's not exactly how it works, but you can imagine that idea. So the other thing you can do is that if you are if you're creating a hash set and you have a pretty good idea of how many items will be in it, you can actually preset the size. With capacity, it looks scarier than it is, but we're basically saying use the fx hash function and assume that we're going to get basically arguments.length entries, because like it wouldn't really matter, but like the point is we're probably going to insert arguments.length items. And so if we tell Rust ahead of time that that's the number of entries that we should expect, it will pre-allocate that capacity and avoid a bunch of resizing inside the loop. So again, I'm going to prove to you that this is actually faster, like with some benchmarks after. But we're just talking through like how I look at this function and think about the things that we could change. So the next one is also very interesting, a little bit more dramatic of a change, maybe. Often, when you're working with small sets, it is faster to use a vector rather than a hash set. So in the previous example, this is a totally different function basically, but in the previous example, you're iterating over the arguments. And if you've ever done like a leak code interview, or you've ever taken like algorithms or anything like that, you'll immediately think, of course, you have to use the hash set. Like it's O of 1, it's like constant time insertion and lookup. So we're just iterating over the data. But it actually turns out that if you have a small number of items, it can be more efficient to just use the vectors directly. And this is pretty counterintuitive. And there are different ways to think about it. I guess like the simplest would be that for a hash set, for example, to iterate over it, you often typically, depends on the implementation of it, but a couple different things could be going on. So one, the entries may not be stored in contiguous memory. This is a little bit of a topic, but I think the Rush hash set actually is. But with a vector, you're guaranteed to be looking at like contiguous blocks of memory. And so when you loop over those, it's very cache friendly because you're just moving along in memory in a way that's very predictable to your machine. Whereas with the hash set, like entries could be stored anywhere. Again, I don't think this is actually true of the Rust hash function, but it's just one way of thinking about why this could be different. The other thing that is true of the Rust hash function is that, or the hash map, is that the hash map has to iterate over empty entries. So I talked about how the hash set or hash map will resize periodically over time. That means you have a bunch of like free space for new things. And so when you iterate over it, I believe that the Rust implementation has to iterate over those empty entries as well. It knows they're empty, and so it skips them, but it has to go look and check. And so the point is, there's just some amount of overhead, some small amount of overhead, let's say, associated with using a hash map. And counterintuitively, even though this is quadratic because you're looking at every element compared to every other element, counterintuitively, this can like actually be faster if your n is very small, and we'll talk about that in a second. And then I think there's one more way to improve this that I thought about, which is man, I feel like this is so lame, but basically, when you access a vector in Rust, the compiler sometimes needs to perform what's called a bounds check. So what's happening here is like we have arguments and then hard bracket I and then hard bracket. We need to make sure that like that is not an out of bounds access. And so the compiler will insert, when it generates assembly, it will insert these bounds checks. So there's some overhead with actually accessing that element because it has to check, oh, is it actually safe to do this? Okay, now I can do it. And this is so funny because I literally never do this, and I see people do it in talks, and I had to do it myself. But basically, if you put this function into the compiler and look at the generated assembly, you can see on lines like 240 and 257 on the right, we have these panic bounds checks. So you can actually see in the generated code that the Rust compiler, or sorry, I guess the runtime, whatever, is having to do these bounds checks in order to do that. And that is slower than if we didn't have to do the bounds checks. So one way to avoid bounds checks in general is to use the iterator API. So if you've seen Rust iterator API, this is like the exact same logic, but we're just writing it in terms of an iterator. So we're saying enumerate over the items and then skip the first I+1 items and compare them. So we've rewritten the same thing, but instead of doing array accesses, we're using iterators. And iterators generally are, maybe always, I don't know, they're able to avoid the bounds check. So you can actually, we should expect this to be faster than the previous version. Which is cool. There's other ways to get the compiler to avoid bounds checks, but I'm not smart enough to like know what those are, how to do them. Like basically, like you can still do accesses, and sometimes the compiler can know that it's actually safe and get rid of those. But I don't really know like what the conditions are under which that's true. All right, so we talked through 7 different versions of this function, and now we're just going to look at the numbers for how they perform. So I think I used 6 arguments, which even felt like on the higher side of maybe of how many a function would typically have, but we're looking at a vector or a slice of 6 arguments. So I benchmarked this with Criterion. So this is the original version. It's 314 nanoseconds. Just getting rid of the allocation, that's the first thing we fixed. We got rid of the allocation. Just getting rid of the allocation cuts it about in half to 144. So that's already like a great improvement. The next thing we did was we combined the contains and the insert into a single operation. That cuts it down another, I guess that's like a third of the 144. I don't know, I can't do the math. We went from 314, 144, and 98. The next thing we did was we moved to fx hash set. So I said we're going to use a faster hash function. That actually got a little bit slower. So now we went from 98 to 103. That's probably within noise. You could call it like the same, but it wasn't a big improvement. The next thing we did was we pre-allocated the hash set size because we knew how many arguments we'd have. That's a pretty dramatic improvement. So that goes to 57. So again, 98, and then it went up to 103, and now we're down to 57. As a reminder, we started at 314. So we went from 314 to 57 just by changing out the hash set, changing out the hash function, pre-allocating, removing allocations, combining the insertion in the contains. So this is the fastest version of that uses a hash set that we will see, 57 nanoseconds. So it's like 6 times faster. We didn't change anything about the API. We just changed how we're working with the data. So as a reminder, the next example is going to be the arrays. So the arrays for 6 arguments is 21 nanoseconds. So it's actually like quite a bit faster than the hash set. I guess looking at it now, it's not just that about the iteration, it's also that we don't have to build the hash set itself. So we don't actually have to allocate that space for the hash set because we're just iterating over the arrays. But we went from 57 to 21. So that's like, again, that's like pretty dramatic. Now we're down from like 350 or whatever to 21, which is a really big difference. And then finally, we had the bounds check and we moved over to using iterators. And so that again, that went to 19. So we went from 21 to 19, which is small, but that's a 10%. That's like a 10% improvement because we're now dealing with smaller numbers. So it actually is a noticeable improvement. The funny thing is, I did this with 6 arguments. If you go up to like I then went up to 1,000 arguments, and the array-based version is starts to be, I think at 1,000 arguments, it's 100 times slower than the hash set based version. So like we saw here, we can use, if we just iterate over the arrays, it's like 3 times faster, but that stops being true if you have large numbers of items. So there's a lot of, I think there's like a bunch of like specific and like maybe higher level lessons in like walking through this function. But a couple of things I would say, like always avoiding allocations, just like I just like always avoid allocations, and you always want to avoid allocations. It's much better not to make copies and not to work with own values if you don't have to. That's the very first change we made. And that's just like table stakes for like thinking in Rust, in my opinion. It's like you're always thinking about ownership, like who owns the data, and you're trying to avoid having to create copies. Avoiding unnecessary work, we like just knowing the APIs. We removed that contains insert into a single insert. That's just knowing the APIs better. And then like knowing your data and like using the right things for your data and benchmarking are like both extremely critical, because I showed you here, like these are benchmarks, but they're benchmarks on a very specific, small numbers of arguments. And if you were to go take this and put this in production somewhere, and then you don't realize that actually most people have like 1,000 arguments to their function, then you're going to ship something that's like really, really slow. And so what is actually the best way to do something? Like what's the fastest way to do something? It actually totally depends on your data sometimes. And we don't do this, by the way. We use the hash set version because I think this difference to me is not nearly as important. Like 57 versus 20 or whatever, and this will scale to like arbitrary sizes. So we don't actually do this, but like I guess in some places we do say we're going to use a vector instead of a hash set because it's faster and it's going to be really small. But like in general, this is not like a rule of thumb for us. My point is, like, what's going to be fastest? It really depends on your data. You have to like think about what the data is going to be. You have to look at actual real world workloads, and you have to benchmark, because the answer to like which of these is the fastest is just like it depends. It's like with every problem you've ever worked on in programming. Like what's better? Like it depends. And it depends on the data and the workloads. How am I doing on time? Can I keep going? I know we're over. I look to you, Alan. Thumbs up. Keep going for a couple more minutes. Okay. All right, so we're not going to go into this much detail in any more examples. I just thought this was a really, really good example because I looked at this function and I just felt totally differently about it than I probably did a year ago. let's talk about a couple other, these will be much smaller. We're not going to go through like huge examples. I'm just going to talk about a couple things that are kind of interesting. And I have a lot of them and I probably won't get through all of them. So one thing we do in Ruff is we swap out the allocator. We use a custom allocator that basically looks like this. You should not go and necessarily do this on like all of your projects. Again, you should benchmark it and see what the impact is, because it is the case, you can see from the benchmarks here, that using a custom allocator actually like greatly improved performance for us. But whether that may not be true on your project, like you have to benchmark it, because I'm not an expert in like which allocator you should use and when, but my understanding is that they all have different strengths and weaknesses, and it doesn't always make sense depending on the patterns of your tooling or your library to like use a custom allocator. It also comes with the costs. It's like more code size, probably a larger binary, like more dependencies. So this is not like a free thing, but I have seen other tools do this. We do this to great success. It's never caused any issues at all, and it improved performance a bunch, which is very cool. So it's crazy that Rust lets you. It's crazy to me that Rust lets you do this. But anyway, we use a custom allocator that made Ruff a lot faster. Kind of cool. All right, here's another fun one that is maybe more complex than is going to be worth it given how little time I'm going to spend on it. But so we have this frequent thing where we need a representation for like a path to, let's say, like a function in a Python project. So imagine like the dot separated path, like foo.bar.baz or whatever, like the thing you would import. We need some representation of that path. The way that we do that is we use like a slice or a vector to represent it. So we have like a slice of the first element would be foo, the second element would be bar, the third element would be baz. And we kind of like use those everywhere. It turns out that it's kind of expensive to be creating and destroying vectors like that so much and so frequently, because you're just doing a lot of heap allocations. So you're like let's say we're doing this like 10,000 times, and we're just like churning these heap allocations. We're like creating and destroying objects really quickly. There are a bunch of libraries out there that do very interesting and clever things for vectors and vectorized data. The one that we use is called smallvec, and it's pretty interesting. So basically the way it works is when you have a vector, like you don't know how big it's going to be. So you want to put it on the heap because it might grow eternally, and you can't fit all that. The stack has like a limited size, and you just can't be like putting arbitrary amounts of data into the stack. So you typically, when you have like a vector or anything that's going to grow in like an unbounded way, you want to put it on the heap. Smallvec lets you put arrays or vectors on the stack up to a certain size. So it basically means that if you're creating small enough vectors and you put some kind of cap on the size that you're willing to tolerate, you can just put them on the stack, which is way faster if you're just creating and deleting them constantly. So we moved those representations from actual Rust vector standard library vectors to smallvec, and it made the entire Ruff project like 10% faster, which is crazy. I mean, it goes to show you that we are creating way too many of these, and I have like, that's like a totally separate problem of like why we are creating this thing so many times. But this is kind of cool. This is like, the lesson here is not you should go and use smallvec everywhere, because again, it depends on your data. You need to look at like how you are using what, and go benchmark on real workloads. Like we only use smallvec for this one struct. We don't use it like throughout the code base. And there are a bunch of reasons for that. Like it's faster if you're creating and deleting a ton of vectors, but it turns out it's actually slower in a lot of cases because you have this overhead of asking, okay, I want item number 3. Is that on the stack or the heap? So there's some overhead associated with it. There's no free win, right? If this was like always the best thing, then it would probably be the standard. But there are lots of things you can do if you think hard about like where are you spending time. There are clever data structures that you can use that take advantage of these ideas around memory and allocation and heap and stack. And so we actually saw like a huge improvement from this, which is awesome. This is just the crate. I don't know why I included this slide. I just talked about it a bunch. Okay, this is another kind of fun one. I already talked about the call path thing. So this is like a path to a symbol, like foo bar baz, or like I don't know if you've I don't know how many people have here written much Python, but like um, I don't know, collections.default dict, that would be like collections, then default dict. That would be like the call path. So it tries to represent basically a unique identifier to some symbol in Python or in your project. And we need to match on these things like all the time. Like if we're trying to figure out if like a function call is let's say we're trying to figure out if it's a specific function call, like actually you're initializing a default dict. That means for every call in your program, we need to see if that call path matches default dict. So we're just like constantly checking against these things. And the way that we used to do this, which in hindsight is, I guess, kind of stupid. Well, I guess I'm just saying that because it improved performance a lot, but like it's more intuitive to do it this way. So the red is what we used to do. So if it was like, okay, we need to know whether a function call is a blocking HTTP call. So if its call path matches any of these, then it's a blocking HTTP call. And then we would do is we'd iterate over this list and say like, do any of them equal the current call path? Because that data is static, we can actually just write that as a match statement. So this is the exact same lookup, but written as a match statement. So if you look at the top here, there's like, we're only really looking at like 3 modules, like HTTPX, requests, and URLlib. And so I've just taken that same thing and rewritten it as a match statement because that data is static. It doesn't change. This is like way faster if you're doing it a lot for a bunch of reasons. Like one, it doesn't have to do nearly as much work because you just match on the first piece. And if it's not requests, there's no reason to check. Like here, we're checking request.get. Even if the first part is not requests, we're going to end up checking all these, right? So the match statement lets us short circuit and skip like a ton of work. And the Rust compiler also like is very good about optimizing these kinds of things. So when again, this improved performance on a Ruff by like 10%. That's crazy. Like we did this in a bunch of places. It wasn't just this one snippet, but we had this pattern like everywhere. And one day I basically realized, wow, we're spending like a lot of time like doing these checks, and I just rewrote them all as match statements, and it made a huge impact. So I don't know what the lesson is here. For me, it was like just thinking hard about what's static and what's dynamic, because we can't structure the code this way if these are like user provided functions, for example. Like we can't write a match statement if like the user is providing a bunch of configuration options that specify these. But if they're hard coded, like let's take advantage of the fact that they're hard coded to like speed things way up. This is like a really, I mean, I don't want to say any of these are like obvious or beginner ones. I guess I can because they're all mistakes I made, but and so I feel comfortable like saying that. But like, this is, you have the same problem in Python and I think in other languages too. But compiling a regular expression actually has like a non-trivial cost. And so here we were compiling this for every single line in the program because we were running this regex over every single line in the program, and so we were compiling it for every single line in the program, compiling it once with this lazy construct. I don't know, it improved performance, let's see, 10 times from like 253 milliseconds to 222 milliseconds. It's like a huge importance improvement. Better than that, avoid regular expressions. If you like really, really care about performance, don't use regular expressions at all if you can avoid it. This is like another thing that we've done a couple times. I don't even want to go through the details of what happened here, but like basically we had a regular expression for identifying suppression comments. These are like little comments that you add to say like, ignore this violation, ignore this violation, ignore this violation. And I got rid of the regex and rewrote it with just some like handwritten, I don't know what you would call it. It's like Lexer code, like parser code. It's just doing the same thing, but it's kind of unrolled. And this is like way faster. And the Rust regular expression crate is extremely good. It's like very high performance, but regular expressions are super powerful. Like they're really dynamic. They can do a lot, and they can't always take advantage of things you like know to be true in the patterns, or things that you know to be true in your data. And so sometimes rewrite it if you have like a very simplistic pattern. Like here, I know that it always has to contain this like no QA thing. So the way it works is we look for those no QAs and then just try to see if it's part of a comment, as opposed to running a regular expression. So again, you should not go and remove all your regular expressions. We still have a bunch in Ruff, but like if you have hot paths that are running regular expressions and the pattern matching is very simple, regular expression might be overkill, and you can actually get better performance by not using it, despite the fact that the regular expression crate is extremely good and can identify some of these optimizations internally. I'll skip this. Let's see. What else is interesting? This is very interesting, but do I have time to talk about it? Okay, I'll talk about this one because I really like it, but I promise this will be kind of the last one. If you have like a Python file and you're like looking at some source code, let's say you have like a function like def foo or whatever. There's two ways to think about like the location of that function. One is the row or the line and column number. And that's what we as humans tend to think about, right? It's like, oh, this function's located on line 4, and it's indented 4 spaces. So it's like line 4, column 4, or depending on whether you're 0 or 1 indexing. So that's like the human representation of how we think about like where something is in the program. The other way to think about it is the offset of that code in the string. So if you have like a big string of source code and you want to know like where the function, and you want to like grab the source code for that function, knowing the row and column is like pretty unhelpful because to find line 4, you have to basically parse the entire, you have to look through for all the line endings. So like, if I gave you a string in Rust, and I was like, hey, go grab me the function that's on line 4, column 6, whatever. That's going to be pretty expensive because you need to iterate over the entire string, find the new line. So, okay, I found the first new line. Okay, I found the second. Okay, I found the third. Okay, now I'm going to eat like 4 characters. That's a pretty expensive way to like do string slicing. And that's actually what we used to do in Ruff. So in Ruff, all of our AST, all the nodes that we worked with used rows and columns because that's what, that's because it's how humans think about like location. And we need them when we report diagnostics. So if we tell you that there's an unused import, you don't want to know like the byte offset of that unused import because it doesn't mean anything to you. You want to know the row and column. So originally, Ruff's syntax tree used these rows and columns everywhere. And Mika changed it so that the syntax nodes all store these byte offsets. It's good for a lot of reasons. Basically, it means that when we need to extract source code, we can do it for free. We don't spend any time like counting new lines. We just say, oh, we need this function. Okay, it's from bytes 100 to 150, and that's an O of 1 operation. We just slice into the string, and it turns out we do that way more than we report diagnostics, right? Like we report the diagnostics to the user because we still have to translate back to the row and column, right? To tell the user this is line 4, column 4. So we still have to like do the inverse operation, but we do that like one time at the end of the program. And most files don't have any violations. So for most files, we don't even have to do that. So it turns out that using byte offsets throughout Ruff and then translating to row and column at the end was way more efficient. This was like, there's like, Mika has like amazing benchmarks in this PR because he's like so good at being extremely thorough, but I guess I lost them. This was like a 20% improvement or something like that. It was like a really dramatic improvement. The other thing, I guess the other lesson here is like, here we're storing a row and column as 2 U32 integers. A byte offset, we just store 1 U32. So it sounds really small, but we're actually we have to store one of these for every single thing in the source code, every single token. And so cutting that amount of memory that's required there in half, also valuable. But the real thing is thinking about like, what are you doing a lot? Like what's expensive and like how often are you doing it? And inverting that pattern here made like an enormous impact. So just thinking about the way you structure your data, the things you're doing a lot, the things you're doing sparingly, what can you afford to be expensive? What can you afford to be cheap? And then ultimately like benchmarking very rigorously to understand it. Okay, last thing I'll mention, and this is the opposite. This is a change we made that actually made Ruff a lot slower intentionally. So in Rust, you can set your release builds to have this like panic abort property, which is sort of a cheat code to make your Rust program a lot faster, because it means that if you panic, if you do something that's like super illegal, your program just crashes, and it doesn't tell you like what happened or where you crashed and why. It doesn't have like a trace or anything like that. So that makes your programs faster because well, I can't speak to the exact reasons because I'm not an expert in that, but like, for example, it doesn't have to do a bunch of bookkeeping to like to be able to play that traceback to the user. It can just it just like decides to fail and like, okay, that's fine. The whole program failed and crashed. And so if you enabling panic equals abort makes your program a lot faster. But for us, it comes at a cost, which is that if people's programs panic, there's no way for us to handle that gracefully. Like we can't like show them a message that says like, Ruff crashed, please file an issue. We're really sorry. Like, here's the trace, include these things. Instead, the Ruff would just crash and just get some scary message that's like seg fault or whatever. And you'd be like, okay, this is a bad experience. So I did this change initially because I was like, oh, I want Ruff to be as fast as possible. And this is the thing I can do to make it fast. And we ended up rolling it back. And we regressed performance by about 15% so that we could show users panics. So we could catch and show users panics. And that to me is a really good trade-off. But this is just to say that like, sometimes you do things to make the program faster, but you've got to think about the big picture. Like not every optimization is worth it. And to me, being able, a 15% performance regression is actually worth it for being able to give users a good experience when we make big mistakes and tell them like, file an issue, blah, 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 blah. But maybe someday we'll get so confident in Ruff's performance that we will be very confident that we will never panic. And then we get a free 15% win. That's the way to look at it. Because we'll do this again. Okay, that's everything I had. You got two really pretty slides at the start and the end, and then all the rest is Keynote defaults. But I hope that made some sense. I'd love to not now, I guess, but please reach out to me on Twitter or on our Discord. And I'd actually really love to get feedback on like the things that you thought were interesting in this talk, the things where I moved like way too fast, the things I should have gone deeper on, the things that just like were really boring. Because again, I prepped all this over the weekend. This is entirely new material. I've never presented any of this before. And I think I see like inklings of things that could be great talks. I'm sure it's not there yet, but I know I'm trying to cover a lot. So I genuinely mean, I just really love feedback. If you reach out, message me, tell me what you liked, what you didn't like. And I can probably stick around. I know we're way over time, so you're definitely welcome to cut us off. I can probably stick around for like 15 minutes-ish.
Charlie, you should be able to unmute yourself now. I think we have a couple of questions as well.
Cool.
Oh, you can. Good. Sorry about that. It's the next thing, not a Zoom thing. The first question, I have a couple of questions here from P and from F. Diego, but first, people are asking me what the benchmark tool that you used was.
Oh yeah, totally. So for which part? Well, there's a bunch of different ones. So we use, I'm actually just going to pull some things up. So we use two tools. So the first is called, okay. Okay, so this tool here is called Hyperfine. This is just the actual PR from something that I showed in the talk. This is called Hyperfine. It's just a generic benchmarking tool, as in it'll benchmark anything that you can run on the CLI. So you say like, and here we're benchmarking, a release build. So run the release build and then just, make the release build and then just run the release build directly. Yeah, Hyperfine, really, really good tool. You can use it again for benchmarking pretty much anything. Oh, also random comment. I guess this probably gets said a lot, but it's never worth benchmarking debug builds in Rust. You always need to benchmark release builds because the performance characteristics are completely different. And release builds are like 10 to 100 times faster than debug builds. Rust is like very, very heavily optimized towards fast release builds, like at the cost of other things. So like Rust compile times are really long in general, and that's kind of that. My understanding is that's basically an intentional decision because they do more optimization passes, blah blah blah. So like in Rust, the release builds are like the thing that you really care about. And so anyway, don't benchmark debug builds. You will like be confused and you will see confusing results. Always benchmark release builds, which is really sad because it means to benchmark you need to do a bunch of release builds, and release builds are take a long time. But sorry, this is Hyperfine. The other thing that we use this is for like, we want to benchmark all of Ruff on like these two code bases. The other thing we use is a tool called Criterion, which is pretty popular, which we more use for micro benchmarks. So this will this is actually a Rust crate, and we like define the functions we want to benchmark, and then it runs them, and it gives you like really, really good data on like how different it was. Is it statistically significant? Like, I don't know if I can find the output, but the output's very pretty. So yeah, we use Hyperfine and we use Criterion as our two benchmarking tools.
Thanks. P, I think you have a question there. You should be able to unmute yourself now. Sorry, I was out from earlier. Maybe the question. F. Diego had a question.
I can also see the chat if anyone puts a question in the chat. I'm now seeing that there are some questions there. Here's one that I guess I didn't get to, right? So someone, Elena Critic, said, Ruff uses a custom fork of Rust Python's parser for tokenizing and parsing. By saying that there's a lot of room for improvement at the parsing stage, you mean there's a lot to improve in Rust Python parser's performance? Yes, I think so. There's, I guess, for a couple of reasons, like, sorry, now I'm like reading, that is like a bunch of interesting questions here. Okay. Arena, do we use arenas? Okay. Yes, I think there's a lot of room to improve the Lexer and the parser's performance. We use a fork of the Rust Python parser. We've actually forked it pretty heavily these days. I think the reasons that it can be faster, well, intuitively for me, it's like two things. It's like one, we have much more of an explicit performance goal with regards to parsing and lexing, whereas Rust Python as a project, they have very different goals. Like the goal of Rust Python is to build a Python interpreter. And so like the parser and the lexer is like one piece of a full Python interpreter. And so part of it's just intuitively that like what Ruff's needs like for the output of the AST are very different. And I think that if we look at the parser and the lexer from that perspective and from a very performance-oriented perspective, I just kind of believe that there's room to optimize it because it hasn't been fully optimized. I guess one example of that is the byte offset thing. So, we're storing rows and columns, and now we're storing byte offsets. The row and column thing, that was actually like a much more amenable representation for Rust Python because like they didn't really care about the byte offsets. They help them that much when they're as an interpreter. Whereas for us, we're constantly like slicing source code and like manipulating it and stuff like that. So that's an example where like the design of the AST, what was optimal for the tools was just a little different, and we could build something that was more performant for what we wanted. The other thing is the Rust Python's parser uses a parser generator, which is totally cool, but I tend to believe that we could, if we were willing to hand write more of the parser, that we could probably optimize it more to our use case, because a parser generator is a very general thing. It needs to be able to generate like lots of parsers, and like we can take advantage of like the structure of the AST in different ways. So I do think there's a lot of room to improve the performance there. And we've actually like have some pretty interesting PRs that might have actually been merged by now, but I kind of don't want to like, I don't want to like blow up Mika by like showing those PRs because like, but but we've already improved it quite a bit, I think, over the course of the past few days, and I think we can improve it a lot more. Just Ruff use arenas. No, we don't use arenas for AST nodes. We might in the future, but we don't right now. We tend to right now. I kind of want to explore doing that in the future. There's like a lot of other small things that we can do for the AST that we could get into, like talk about like enum sizes, like boxing variants is something that people do a lot. This probably sounds like total gibberish if you haven't like written a lot of Rust, but like the size of an enum in general is roughly the size of its largest variant. And so if you have like one really big variant, then no matter what you instantiate, you're paying that memory cost every time you allocate it. And so you can think to reduce the size of your objects and all that kind of stuff. Sorry, I'm kind of going off script. Okay. Any other questions? Anything else I can answer?
Is anyone able to activate their mics, by the way? Sorry, can you hear me?
Yeah, I can hear you.
So you're squinting like I'm very, very quiet. Am I?
No.
Okay, I can't hear myself, obviously. Yeah, are there any other questions? I mean, you could try and if you want to ask a question, you can try and unmute yourself. That's enabled now. Someone said, I learned loads. I was waiting for somebody to suggest PR 5554 is potentially also a discussion about writing more specific regexes.
Oh, funny. Like an actual one that I showed. Oh yeah, okay. That must be someone, I don't know who that is just from the name, but,
Yeah,
it must be someone who's, I no.
Yeah,
but I don't know.
the
Must be someone who's
quite
hanging around the
avoiding
repo.
just P, but anyway. Oh, here we go. There's another message.
Sorry, the chat moved, didn't it? At work, we get more questions after closing the recording. Oh. Actually, I was just realizing this is the criterion output, by the way. So I talked about criterion before, but it'll be in your terminal and it'll have nice colors, not like this.
Actually, I have a question. So for performance analysis, have you used tools like Valgrind or Flame things, or have you used something that would give you like per kind of call performance statistics, like sampling and things like that?
Yeah, totally. So I use yes, I use instruments because I'm on Mac OS. But we actually have instructions. I mean, if anyone's ever trying to figure out like how to benchmark their Rust project with like I can't remember if it's called flame graph or perf graph or whatever, or instruments or whatever, we actually have instructions in our contributing.md. They're probably more generic than just applying to Ruff around like how we use those tools. Those are really useful. That's like a whole skill set in itself and something I would like to get better at, like learning how to actually use those tools. And I'm starting to get better with instruments at actually looking at the flame graphs and like digging into specific functions and trying to understand like what's inlined and how do I understand improvement. But yes, that's also like that's also a very valuable practice and probably something I'd like to do more of, but I'm still trying to like get good at those tools.
Actually, speaking of, since we're sort of on the topic of Python as well, there's a version of FlameGraph called for Python called PySpy, which I found very useful.
Oh yeah, I think PySpy is written in Rust. Yes, it is.
I think it is. Yeah.
Yeah, that's a cool project.
So any more questions? I mean, we can pretend we've closed and then people can ask their questions and then we can ask them and say, we haven't finished. No, okay. Well, Alan's microphone's packed up, so yeah, you can do signing. I can't read signing, so I can't tell anyone what you said. But yeah, thanks very much. That was an excellent talk. Very enlightening. It's a great project. It's lovely to hear from from someone who's written such a high profile and very widely used project.
Yeah, thanks a lot. No, this is really fun for me. I really appreciate it. I hope it wasn't like too high level and then too low level or anything like that. Like I said, very open to, if you want to DM me things that you liked, things that you thought were interesting, would be helpful for me in the future. Yeah, thanks a lot for inviting me on, and for everyone for sticking around, listening, asking great questions. Yeah, it doesn't have to be written in Rust to be a cool project, by the way, but this sort of this Rust Python hybrid community, I think, is it exists, but it's pretty nascent. There's some other projects in Python that leverage Rust in interesting ways. And so I just like to champion those projects, because I at least believe that Rust could be a big part of Python's future. And so I like tools like PySpy. But yeah, I am biased in that I will probably think something is cooler if it's written in Rust, but it's not a strict requirement. Cool. All right. Well, thanks everyone.
Yeah,
and
thanks for coming.
have a great evening.
Thank you very much.
You too. Thanks very much.
Take care.